Hi, good morning, good afternoon, good evening to wherever you are located. My name is Dr. Vishwanath Hegadekatte. I'm the R&D Manager working for Novelis Inc. Today, I will be talking about streamlining materials design with intelligent experimentation. My co-authors for this presentation are listed in this slide. I'll move forward from there. I want to give a brief introduction to Novelis. So Novelis is the world's largest aluminum rolling and recycling company. It is the world's largest non-ferrous company, and we have operations in four continents and in several countries across these four continents. Um, we have about 14,500 employees. Our revenues stand at about $12.3 billion in 2009. Our EBITDA is about $1.7 billion, and as I said earlier, we operate in four different continents across 9 countries, and we have 33 operations across these 9 countries. No, Novelis, the product segments of Novelis are divided into beverage cans, automotive, aerospace, and specialties, as shown in this slide. And in each of these product segments, we serve some of the world's who's who in the business, like Anheuser-Busch InBev, Coca-Cola in the can segment, Ford, Land Rover, Toyota, BMW in the automotive segment, and in aerospace we supply to Airbus, Boeing, and in specialty segment we supply to Samsung, Denso, LG, um, uh, and and many other companies which are not listed on the slide. So, with that introduction to Novelis, I would like to introduce the topic of discussion today. Um, the objective for this work for us was basically to develop a capability for fast and efficient optimization and design of experiment in an R&D setting where explorations are expensive. These explorations can be computational as experimental, like conducting a lab trial or a trial in one of our plants. So the value proposition for this work is that we are basically aiming for reducing the cost and time for reaching our project targets by reducing the number of observations in the design of experiment setup. So what do what do we so what how does our optimization problem look like? So generally we have a target. Let us say it is the strength of our aluminum alloys, flat roll sheets, and we have several knobs to turn. By that I mean we could change the chemistry, we could change the thermomechanical processing route, make changes in hot rolling, make changes in cold rolling, make changes during solutionizing, and things like that, all through the process. So all these knobs, they are there for us to change to achieve the the targeted strength in the material. Now in order to do that, so to get the best possible strength, now we need to solve the inverse problem, right? So then this becomes an optimization problem to solve. So what is the question then is, what is the most efficient design of experiment? So what do we do currently? Is I mean, it is not just Novelis, it is across most industries. You will see that companies use a fractional factorial design of experiments or full factorial design of experiments, where you get a polynomial function at the end of this, and based on your intuition and domain knowledge expertise, you run trials that are most likely to hit the response targets. And tools like Minitab give you this effects plot where you can where one can understand the effect of one parameter or a combination of parameters on the response. Now the question is there a better way of doing this? This is a lot of experiments that need to be conducted, even if we are using a fractional factorial design of experiment. um, so for this audience, I don't need to really explain what Bayesian optimization is. This slide was mainly created for Novelis internal use, but nevertheless, we within Novelis's R&D group, we believe that Bayesian optimization can be a better alternative than using um, yeah, using Minitab or this fractional or full factorial design of experiment. So the basic steps for using Bayesian optimization is basically you end up fitting a surrogate model, and then you find the most promising regions and then probe those most promising regions, and then the whole process repeats. The most promising regions are determined by looking for regions which have the most uncertainty. So that's the uncertainty quantification actually becomes an integral part of this method itself. And there are some key differences with from traditional design of experiments, where the generalized functional form is available here when using Bayesian optimization. And Bayesian optimization is best suited for when experiments are conducted sequentially, so one at a time, so that the surrogate model can learn from each experiment. Oftentimes in a company like Novelis, when we conduct trials, we need to run batches of experiments. We cannot really afford to do one experiment at a time. In the And this is for physical experiments. For computational trials, yes, we could easily use sequential trials. We'll talk about all of that with several case studies that I'll be presenting in this section. Um, the first case study that I wanted to present was on beverage cans. So, as I said earlier, Novelis is the world's largest producer of flat rolled aluminum sheets. 50% of our revenues come from selling flat rolled aluminum sheets to the beverage can market. And as you can see, the modern beverage can is a highly engineered product. Uh, in fact, I can easily say that this is one of the most engineered products that you will ever lay your hands on in day-to-day life. And the next most engineered product is probably the space shuttle or something like that. Nevertheless, here what we have within Novelis is a formidable capability in modeling beverage can making using the finite element method. So the finite element method is a computational method for understanding the mechanics of deformation during can making. So each of these finite element models, they take several hours of computational time. And what we have done is that we have actually parameterized the beverage can geometry as shown in the pictures here. And we have about 40 odd parameters in this model. Sorry, it's written here, it's 26 parameters that we have. And the target response that we are after is the best possible dome reversal pressure that is shown in the animation here, the pressure at which the dome actually pops out. The bottom dome of a beverage can pops out. So if we were to run these finite element simulations just for the min and max of each of these 26 variables, we will end up with like 67 million computations. And if we add a center point to that computation, then we'll end up with with two times e raised to 12 number of computations, which is roughly 147 years of finite element computations alone. So that is not the way to go. If our aim is to find the best possible design that will give us the highest design of experiment, we actually thought that we should be using a more intelligent way of solving this optimization problem, and that's where we started using SigOpt. Here is an example where we ran where we ran a grid search of 15,000 simulations, and the highest dome reversal pressure that you see, this is in bars now. The highest dome reversal pressure was somewhat like a 8 point odd bar, or it's actually around 7.5 hours, and this was out of 15,000 simulations. And what we did was we started using SigOpt, and we saw that we could actually achieve this a better result with a fraction of the number of simulations that we had already spent by using grid search. So actually, there were in this model there were two target properties that we were trying to optimize. One is the dome reversal pressure, which is shown in the animation here, as I said earlier, and the other one is the column strength of the beverage can. So how much load can a beverage can actually take when you load it actually. So that's what is plotted on the x-axis here. So here is an example where with we using SigOut with the least number of computations or observations, we were able to find a better design than what is currently commercially available. So the next example I wanted to show was about an automotive component. As I said earlier, Novelis supplies flat rolled aluminum sheets to the automotive market, and in the automotive market, for automotive applications, crash is one of the most important applications where aluminum is used. And here we were trying to design axial crush component, as shown in the picture here, where I'm showing where my mouse is indicating. So the question what we want is, during a crash event, we want this crash member to actually crush and fold in a known way, like the good case here, and not like in the bad case here, where the column buckles. So in a crash event, if the folding happens like the good case, then the energy is absorbed in a gradual way. If it were to buckle or crack, then the energy is of course absorbed, but not in a controlled way, and that can be dangerous. So the question then was that how do we design this actual crash member? So what should be the height and width and thickness of the sheet? And then there was, of course, being a metal supplier, what are the material properties? So here are several parameters that we need to fit. For the material, we had to fit these various parameters: alpha, K, A, B, and N. And then for the geometry of the actual crush member, we had to find the width, height, and thickness of the crush member. That would give us the highest load factor. Now, if we were to run these computations to find the maxima, then we would probably end up running 45. Running finite element simulation for the next 45 years. Depending on what we were doing, anywhere between 1 to 45 years. Even 1 year is unacceptable. So once again, here we actually used SigOpt, and here we compared with LS Dyna's optimization tool, LS Opt, where you can see that SigOpt helped us come up with a better design that would give us a better load factor, and the number of computations was an order of magnitude lower than what LSOpt had made us run. So here is another example where Bayesian optimization and SigOpt specifically helped us reduce the number of computations. Um, the next example I want to give is that of a beverage can lid. So I've been moving from beverage can to auto and back to beverage can. So in the previous beverage can example, I talked about the beverage can bottom. Now I'm talking about the beverage can lid. So here with the beverage can lid, the aim was basically to find the way the parameters, like we were looking at two different tooling kinematic parameters and two different tool loading parameters for forming the can lid, and such that the geometry of the can lid that gives us the highest buckle performance, that is the pressure at which the can lid pops out. So we want the highest possible pressure. So the can lid should be able to withstand the highest possible pressure. And the question then is, what should be the tooling? What should be the lid geometry that will give us? And in order to get that lid geometry, what should we be changing in the tooling kinematics or the tool loading? That's where we were trying to do. Here is an example of what we did. Various experiments that SigOpt ran for us, and um, as you can see, with SigOpt, we were actually able to design a can lid that would give us a better buckle pressure than our previous designs. This 1 MPa difference is quite a bit in beverage cans. As I said earlier, beverage can is a highly engineered product, and that small difference in the geometry that you can see between the green lid and the black lid is what results in the difference in the performance of the can lid, and that's what we were after. This, mind you, is an example where we just had 4 parameters for tuning. In reality, we have like almost 100 parameters that needs to be tuned, and that's a work that is currently ongoing. um, Another case study that I wanted to present was where we were, I mean, this the case studies that I presented so far were on product design, the products that our customers make with our flat rolled aluminum sheets. Now here is an example where I'll be talking about our Novelis product, which is a flat rolled aluminum sheet. So here we have a we perform thermodynamic computations to compute the strength of the material during artificial aging for our automotive aluminum alloys. And this computation is generally done using a code called thermocalc, and we actually supply the chemical composition, and we supply the time and temperature profile. And the idea then is to find the um, uh, to get the microstructure information during solid solution, and then the subsequent precipitation during artificial aging. And the aim is then to find the strength of the material, the yield strength of the material as a function of temperature and time. So obviously, this model has several parameters that needs to be determined. So we need to find these parameters. And here we used SigOpt once again, or Bayesian optimization rather. Actually, we used Bayesian optimization, and SigOpt was one of the tools that we used. The parameter. So here are the list of parameters. There were about 5 parameters or 6 parameters that we had to tune in order to get the best possible uh, strength in our material. Now we are here in this graph. We are comparing the strength that we experimentally measured in the lab, and the calculated strength from the model I showed in the previous slide. For determining these parameters, we used four different tools. So we used genetic algorithm, we used AX from Facebook, we used Dragonfly from Carnegie Mellon University, and then SigOpt. The results are shown in the next slide. Here you can see that we are plotting log error as a function of trials, and you can see that SigOpt outperforms both AX and Dragonfly. In fact, it reaches the lowest error faster than any of the tools, and the and the error values are lower than any other tool that we used for this optimization problem. Mind you, these are like 10,000 computations we had to do for genetic algorithm, while with SigOpt, to get the same or better result, we just had to do a few hundred simulations. So 10,000 simulations in this case takes about a day's worth of computing. Um, so I mean, we also compared SigOpt with other tools. Here you can see on this slide the number of parameters that SigOpt allows you to use in the model is about 100, and that I believe can be extended. Is that what I learned from my discussions with SigOpt? AX, on the other hand, has no limitations, but their documentation advises not to use more than 20. The metrics, SigOpt has an upper limit of 2 and AX has an upper limit of 5. Dragonfly, on the other hand, has the GitHub repository has not been updated in more than a year, so I don't think it is worth discussing anymore. And the major thing that the major reason why we are using SigOpt within Novelis is basically its ease of its ease of usage. So it has an enterprise level GUI, and as I said, people in my group know programming. They are extremely skilled programmers, and for them to use programs to solve optimization problem is not a problem at all. But what the biggest impact we can make within Novelis R&D is when our experimentalists, our metallurgists and engineers begin to use Bayesian optimization for their design of experiment, and that is allowed with the GUI that SigOpt provides, and that's one of the main reason why we are using SigOpt within Novelis. Okay, as I said earlier in the presentation, we did do some studies on batch versus sequential runs. In a company like Novelis, where we rely a lot on physical experimentation in the lab as well as in our plants, we generally get time slots in the lab or in our plants. And when we get these time slots to conduct our experiments, we need to run it in batches. And so the question then was that if we run in batches, would we get as good results as we would get with sequential observations? So here is a graph where we are actually comparing the two run cases using the aging model that I described a few slides ago. And as you can see here, that if you were to run 10 batches of 15 experiments with a total observation budget of 150 observations, and compare that to one observation at a time sequentially, 150 such observations, you will see that the best value that you get from the batch run is much higher than the sequential run. So this best value is basically the aging model error in megapascals. So lower is better in this case. Well, with that, I've actually come to an end, come to the end of my presentation, more or less. So I have a couple of slides. So this was a slide meant for internal consumption. Modeling case studies that I presented in this presentation are good for benchmarking and actually convincing our experimentalists to use such advanced tools. But optimization problem is optimization problem, and it is exactly the same if you're doing experimental work, as I said, like lab or plant trials. So we believe that Bayesian optimization will most likely give us better results than traditional DOE for limited observation budgets. So if we were to do a full-fledged grid search, yeah, sure, we could probably get better results, but within a limited observation budget, we believe that Bayesian optimization performs much better than traditional DOEs. So I would like to just show this one slide. We've been talking about experimental work and comparing that with computational work. So in a company like Novelis, we have been using machine learning for designing new aluminum alloys, and as you can see here, we basically are able to scrape data from literature using NLP. We have physics based models that generate data, as I've shown in this presentation, and we have experimental data that we have uh, uh, that we have conducted within our labs as well as in our plants. But R&D data is generally a small data set, but it is rich and sparse. And each of these steps in using machine learning for alloy design is much faster, but the rate limiting step is actually the lab trial. And for us to start for us, it takes about 4 months to actually decide which chemistries we want to cast, and then process the material through our labs and test the material, and then collect all that data and feed it back. So the rate limiting step is basically the lab trial, and that's where we believe Bayesian optimization can help us in reducing the number of lab trials that we generally conduct. So with that, I'll end my presentation. Thank you very much for listening to my talk.